Now, today I want to start with correlation and regression analysis. Some of you are disturbing, so I'm muting everybody. If you have a question or answer, you can raise your hand. We want to look at descriptive statistics, correlation, and the basics of regression as a starting point for the bigger ones to look at. We want to start with correlation, but before we start with correlation, we'll remind ourselves with covariance because we'll meet it along the line. Correlation and covariance, both of them look at association between two variables. The only difference is that covariance, the value is from negative infinity to positive infinity. But correlation, the range is from -1 to +1. Both measure relationship, both measure association. The relationship between two variables, there are so many things that relate to each other. The covariance tells you that the value is positive or negative, but doesn't tell you the strength of the relationship. In other words, it's very difficult to determine magnitude, even interpret it. So when you have a value of 400 and another value like 200, it doesn't necessarily mean that the bigger one is stronger because it depends on the unit of measurement. I'll give you an example. If somebody says, I want to give you 200 gallons of water, and another says, I want to give you $200. Question is, which one would you take? If someone says that I want to give you $1 million, and another says that I want to give you 1 million kilometers. So each of them differ by value. If somebody says, I want to give you 1 million millimeters. So the unit of measurement is not accounted for in covariance, but it's accounted for in correlation. So in correlation, you're looking at both direction and magnitude. That is why we always say that correlation is a scaled measure of covariance. Write it down. Correlation is a scaled measure of covariance. Now, as you can see, there are certain things on your screen here that have some correlation. What I want to simply know from you is whether the relationship is negative or positive, just from prior knowledge. Okay. Do you think the relationship is negative or positive? Let's start with age and power of vision. What would you say is a relationship? Age and power of vision is negative. Okay, it's negative. Running time and calories burnt.
It's positive.
Temperature and ice cream or bottled water. Kate. Adult.
It's positive.
Study time and grade. Study time and grade.
Positive. Positive. Positive.
Can you allow people to be answering without raising hand, without help us? Especially when we allow it and it gets to a point where everybody is talking the answers. Study time and grade. Millicent.
Positive, sir.
Price and quantity demanded. A handful. Quachiado.
Negative.
Wage and experience. Wage and experience. Quachiado.
Positive.
Now, consumption and savings. Eileen.
Negative.
All right. You should have these things in your mind. Okay. Now, This is the formula for covariance. That's the one you see. And the one below it is a formula for correlation. To calculate these things, and we shall do that next time, this time, to calculate this, you just need the value for X and the value for Y. So X can be quantity demanded and Y can be price. So you just look at the relationship between quantity demanded and price. As long as you have the column for quantity and column for price, you're done. You can calculate a correlation. As long as you have hours of study and then the grade, it is sorted. So that is exactly what we do. 2 questions so far. Okay. So now, correlation is powerful, but when you have a number, it's better. Correlation, we said, is between -1 and +1. The strength of the correlation is what would, the absolute value of the number of correlation will tell you the strength of the correlation. Okay. So as an example, if you have a number that is -0.92, and you have another one that is 0.91, which one has a strong correlation? Which one has a strong correlation? Which of these two? AC?
-0.92.
Why?
Because you're taking the absolute value of the 0.92, so it becomes a positive number. And then when we compare to 0.91, it's higher.
Excellent. So that is how you analyze correlation all the time. In fact, you have a compulsory question on descriptive statistics and correlation all the time, and regression. So it's important that you are getting it. How do you measure correlation? You use a statistic known as Pearson's product moment correlation coefficient. If the data is parametric, that is what it is. At this stage, you all remember parametric and non-parametric. But if the data is non-parametric, you use the Spearman's and the Kendall. Now let's assume you have a data set I'm about to describe. So you are doing your long essay or thesis or dissertation or project. It doesn't matter whichever way you call it. You are undertaking the topic entitled Determinants of Demand in the Alcoholic Beverage Industry in Ghana. Determinants of demand in alcoholic beverage industry in Ghana. Impact of location, occupation, and religion. So the other variables though, but your focus is on location, occupation, and religion. How these things affect Burukutu, the gin bitters. Now you decide to collect a data set of Burukutu Ventures. It's a local gin distillery. Is highly concerned about the demand for its bitters. Why? Because there are new entrants into the market. So competition is fierce. Management want to know those predictors, those factors that will better explain the quantity demanded of gin bitters. They want to know, aside the price. So apart from the price, there are other factors they believe affect quantity demanded. One of the factors are prices of complement of gin, okay, or the price of the complement. Who can give me an example of a complement of Akbatish? The complement of gin bitters. Who has an example in mind? A complement is something that goes hand in hand with another one. It's a good that is used in conjunction with another good. So for example, your left and your right shoes are perfect complement. We normally say that your Gary and soakings are complement. Even though some people can chew them. Which other complement of gene would you think about? Kate. Kate. Someone.
Sorry. Lime.
Okay, someone.
Please look. Castle Bridge versus Aromobites.
They are not complement. Are they not substitute to other? Or you're confused? So complements of gene include kebab, ice cubes, and so forth. When you watch this video, it will tell you the gene bitters that we are talking about. Now, so here you have a data set, and this is a data set, the quantity demanded of gene bitters. You have the price of gene bitters. You have the complement price of gene bitters. You have the income, the average income of the people within the area you are selling. These are shops. You have the location, whether it is Dansoman or Community One. You have occupation. You know, when you take location, both urban and rural, which one is more likely to be consuming a lot of gene? Which of them is more likely to increase gene consumption? Nana?
Rural.
Very good. Occupation, which one? Teaching, fishing, trading. Nana?
Fishing.
Religion, Muslim, Buddhist, and Christians. Nana?
Muslim.
It is Christians. Christians consume more alcohol than the other religions that are there. However, this is not statistically confirmed until you've subjected all of them to statistical testing. Regression will look at how these things all have a relationship with them. So your job today, we are going to generate contingency table, also called cross-tabulation table. We are going to create summary statistics and interpret them. We are going to be using Jupyter Notebook. I've given you the file already. And then we will look at correlation matrix, the one we just looked at. Now let's try and have a little bit of theory for contingency table. Okay. First, we have to do a descriptive statistics. You can easily do a descriptive statistics of the data set easily. You can do that in Excel. Now, sometimes some people really struggle to do descriptive statistics of the data set in Excel. But even before you do it in any other software, things in Excel should always be basic things to start with. So how about we take the data set, and you can follow along with me. Open your Excel, and then you can do the descriptive statistics. To be honest, I'm not so comfortable doing it, but I just want to show you. Okay. Now for Excel, you don't want to consider the categorical variables. By the way, when you look at these variables, which variables are numerical and which ones are categorical? Which ones are categorical? Which ones are numerical? You raise your hand. I posted a data set on your group page. Do you guys remember? Or you don't have it? Do you or you don't? Yes, talk to me. Do you have or you don't have?
Please, we have it.
We have, please.
Okay. So I'm still trying to post it here in the chat. I've given you the Excel version, but please remember that you have to save it as a CSV file. But the CSV file is on the page, so you can check that. Okay. Now, let's now do some better work. So the numerical data are QPCM, and then the categorical data are LOC, OCC, and religion. That means that we're talking about location, occupation, and religion. Now, you just go to descriptive statistics. How do you go there? Click on the data tab at the top. On the far right, click on data analysis on the far right. And then a pop-up will show. In the pop-up, look for summary statistics or descriptive statistics. Okay. You see descriptive statistics here. Double click on it to open it. And then input the range. That is all the numerical variables. So click on the Q, drag it all the way to M, drag it all the way down to the end. If your data is many, you can use shift arrow down. Once you've done that, take labels and take new worksheet. Under the new worksheet, type something small. Let's say type like result, RES, and check summary statistics. You're done. Click enter or OK. And you can see the new sheet is created. And this sheet that has been created is known as your descriptive statistics. You just have to clean it by first move all the variables one step leftward. And then clean all of this. Hold Control key down and click on the C column here, the E column, because you're all having the same name, and J column. And right click on one of them and click delete. It will delete everything. And then you can now move these ones all to arrange them. Remember, this first column is just the descriptive statistics. So you have the mean, the median, the standard deviation, all of them, you have them there. That is what is known as the descriptive statistics. We'll look at their meanings later. Now, who can tell me why you didn't do the descriptive statistics for the categorical variables? Because they are dummies and you don't need them. They are meaningless. When we come to Python, you get it better, but they are meaningless. So that's how you do descriptive statistics, which we just did. Now, you can also do contingency table. These are preliminary work you should do on any data. Contingency table simply means you are grouping them into categories. So you have categories B1 and B2, and up to whatever B. You will now categorize them and find the total for each one. And you use something called chi-square test to do that. You measure the association. Okay. Now, you will have a column 1 and you have a row. So this one looks at the row sum. And then the next one looks at the column sum. And the final one looks at both the row sum and then the column sum. The next thing in your data is to check whether your data set is normally distributed. I'm just giving you the theories first. Now, how do you check whether a data is normally distributed? So, for example, in our data set, you can just check whether quantity column is normal. In other words, we want to check whether the distribution is normal or the distribution is, left tail in this example. How do you do that? You use a certain test. You use a graph, of course. We shall come to that. But you also use a certain test to do the check. And the test that you use to determine normality is known as the Shapiro-Wilks test of normality. On your screen is a test statistic for the Shapiro-Wilk test. The test statistic is defined as each coefficient multiplied, that is the expected value of other statistics, okay, multiplied by that particular column. And then you subtract that same thing from the next row. And then, in fact, eventually you can simplify the whole thing to be AIXI squared, and then the difference between the mean, we call it the mean difference. The difference between the mean and each observation. You do that, and then you estimate the test statistic. But normally the softwares will do this particular one. So I would rather give you these results and then you interpret them. My interest is in the interpretation. So we'll look at Shapiro test for this data when we come to the Python or the Jupyter notebook. Now, let's go on to regression. Remember that correlation deals with association, regression deals with causality. Regression is basically a statistical method. You use it to establish relationship, make inferences or prediction. What are you predicting? You are predicting an outcome. The outcome is also called dependent variable. You are predicting a target. A target. The target is also called dependent variable. And you are predicting it or you are forecasting using some independent variables. The independent variables are also called predictors or features. Predictors or features. Some of these things you have to write them before you can shoot. And regression can be simple regression or multiple regression. Who can tell me the difference between a simple regression and a multiple regression? Okay. Now, like I said before, you can't be typing from it. You've got to be used to raising your hand and asking questions or answers. It's the best way. It's a communication. Otherwise, when I keep talking alone, you'll not understand. So what is the difference between a simple regression and a multiple regression? Okay. Celia, is it that is my class up here?
Yes, please look.
You are Samuel Obeng.
Yes, please look.
And you don't know the answer to the question I just asked. Samuel, you don't know the answer. Samuel.
Look.
Do you know or you don't?
Please look. I was not able to get the question right, so I don't know.
Okay. Aline, go ahead.
Okay, so I know a simple regression uses just one independent variable to predict a dependent variable, but then multiple regression uses two or more independent variables to predict a dependent variable.
Very good. That is the exact answer. So a simple regression has one feature. Multiple regression has multiple features, many features. So multiple regression is a bit complex than simple. Now, sometimes the multiple regression will have dummy variable, categorical features. That kind of regression becomes a dummy variable regression. Please note that the aim of a regression is to establish causality and to make predictions. That is the main aim, to establish causality and to predict. That's the main aim. Now, this is a typical example of a simple regression. As you can see here, they are all metric. Okay. And then you have multiple regression where the metrics are many. And then you have a logistic regression. A logistic regression is where the dependent variable is 2, as you can see here. Unlike in a multiple regression or simple regression, the dependent variable is 1. But in a logistic, the dependent variable is 3. For example, you want to predict the probability that somebody will default or somebody will have cancer or will not have cancer. You use a logistic regression. Now, let's look at some applications here. The future sales of a product based on the past. You can use prediction or regression. Economic growth of a country. You can try and establish the causality between economic growth and other factors. How much to pay a new employee based on experience and all that. You can even predict petroleum. These are all research topics you will do if you don't have it already. By now, they must have told you to contact your supervisors. These are some of them. Okay, let's try to understand the basics of simple regression. So in a simple regression, we have the dependent factor or the target variable. And you have the beta naught, the beta 1 multiplying the x, and then you have the error term. The independent variable has one job it's trying to do here. You can tell us a job. It is trying to influence the dependent variable. That's what it's doing. So when you're looking at the quantity demanded and price, you notice that price is trying to affect quantity demanded. So price is the independent variable. But then how much price is influencing the dependent variable? There could be other factors. And those other factors are what is known as the epsilon or the residual or the error term. The error term are those factors that can influence the target or dependent variable but have not been captured in the model. That's what we mean by the error term. In fact, the entire regression process is based on this error term. Because the goal of the regression is to ensure that the errors have been reduced to a significant value of 0. We normally say that the expected value of the error term should equal to 0, which means that the mean of the error term should be 0. Remember, the word expected value of any random variable is the mean. So the expected value of the error term should be equal to 0. So when you get the errors, some of them will be positive, some of them will be negative. Your job is to have a proper model that will neutralize all and eventually give it a value of 0. So what is the difference between the specified regression model here and the estimated regression equation here? What is the main difference between these two? Or what do you see as differences? Patrick?
There's no expected error in the estimated.
Yeah,
there's no expected error in the estimated.
What else? Apart from the fact that there is no error term, what is the next thing? We'll notice that the estimated equation has no error term, but yes, Millicent.
It's looking at the mean. So,
what is looking at the mean?
the estimated regression appears to have the mean symbol on.
No, it's not the mean symbol.
Okay.
The estimated regression equation has got the beta parameters here as estimated. So they become numbers or numerical coefficient. So the estimated equation has numerical coefficient. The specified model has Greek letters, not numerical coefficient. I'll ask you this question in exam about the two main differences. So take note. Right. So now, how do you do regression? Well, one way you do regression is by estimating the beta parameters. Okay, let me just go back and show you something. Okay, in the graph that we had here, we have it. Oh, that's it. I'll come to that. I think it's the next thing we are going to be going to. So how do you get this beta parameter? How do you get the values of this? The beta naught, the beta 1, the beta 2, the beta 3. How do you get them? One way to get them is using an estimator. Using an estimator, you can find them. There are a number of these estimators. The most common one is known as ordinary least squares by Legendre in 1800. Ordinary least squares, OLS. What is that? We'll look at that pretty soon. There is also the maximum likelihood estimation by Fisher. Maximum likelihood estimation. There is a generalized least squares by Alexandra Aiken. Generalized least squares. Then there is a feasible generalized least squares. There is a feasible generalized least square. Finally, there is the feasible generalized least squares is also sometimes called the weighted least squares, the WLS, the weighted least squares. So these are all methods that you can use to estimate the coefficient. The coefficient here tells you by how much that independent variable affects the dependent variable, by how much the feature affects the target. It tells you that. Now pay attention here. This is where the real regression starts. So to start with, you have some data set. Okay. I can just do this in Excel actually, using our own data set. So let's just go back to our Excel. I'm just going to use the quantity demanded and price. Remember that in this context here, the quantity demanded is one variable and the price is also another variable. So I'm just looking at quantity demanded and price. Okay, so that we'll have a simple regression. How do you do the simple regression? Well, there are so many ways you can do this in Excel. You can just highlight the two of them. You can just highlight the Q and this. You can do it even with me. Okay. You highlight them. Then under insert, you will see scatter plot. Scatter plot. You will click on scatter plot and you'll try and scatter plot the data. So this is a scatter plot of the data you see here. All of them. Then you go to the far left. You see quick layout. Quick layout. Quick layout. There is a layout which is layout number 9. Layout number 9. You don't click it, hover the cursor on it. And when you do layout number 9, you will see that it will give you the entire scatter plot, the linear line, also called the best fit line. It will give you both of them. And it will also give you the regression equation. It will give you that. In fact, let me click on that. You can click on that. And you can click and drag it. Okay, drag it away. You can click and bolden it. Drag it, and we'll talk more about this. So it tells you that the Y, which is the quantity demanded in our case, depends. Oh, watch something here. This is error. If you want to do it, you want the price to be on the left side. Okay, so I'm going to just delete this. And then if you want to do it, you can just copy these two alone. Okay, take it to a new sheet. Okay. And just move this is only for purposes of drawing. Just move the K to the right-hand side so that the P will rather be on the left-hand side. Okay, you can click inside and do Control A to highlight. And then let's go back to Insert, choose your chart, choose your scatter plot. Okay. And then go to Quick Layout and choose number 9 again. So this is the number 9. So you can see that this one, the good thing is that it tells you the values. In fact, you can click colors and change the colors of the scatter plot. Okay. You can click on this scatter plot here. In fact, you can click here and choose format here. And you can just have a different format. But I mean, this particular format is good. Okay. Click on that. You can change some of the coloring. I don't know why this one is not changing. Hey, there you go. You can change some of the coloring. And just look at this very one here, the equation. The equation is now showing a negative relationship between Q. Q is the quantity, so you can rename it. In fact, let me zoom in. Q is the quantity, that's a Y. So you can rename it as Q. And then the X is a price, so you can rename the X as price. And you can see that the price is negative because theoretically there's a negative relationship. So who can tell me this axis, the vertical axis? Who can tell me what this vertical axis is? Which axis is that? Yeah, question.
Quantity demanded.
You see, when you look at the graph here, the one that came first, that's the price. And in fact, in case, sorry, it's a quantity, it's a quantity. It's a quantity demanded. And one way you can see that is that you look at the values here. The values are in hundreds and 200. And you can see that the axes are exhibiting hundreds and 200. And so let me just write quantity. And when you come here, when you come to the x-axis, is a price. So you can just type price. Okay. So that's it. That's what this very one is showing. I was just trying to show the graph. That's all my interest. And when you look at the graph, you can see that the line of best fit is thrown at these values. And so you know it. Okay. I'm not interested in doing it here. I'm interested in doing it. But that is what regression is doing. So what is exactly regression is doing? Let's zoom in. Let you see. What the regression is doing is that there is a gap. Check it carefully. There's a gap between the scatter plot and the line. There's a gap. Some of the gaps are above the line. Some of the gaps are below the line. Some of the gaps are below the line. Some of the gaps are above the line. Below the line. So those that are below the line, their errors are negative. In fact, you can calculate the errors. Those that are above, their errors are positive. So what the entire regression will do is that, and I'm going to show you mathematically, but I want you to know. First, the errors are sometimes called, they are sometimes called epsilon. That's what we use. Okay. But sometimes you don't call them epsilon, you call them E. In fact, some people even call them U. It doesn't matter. Just know that these errors are called different names. So let's take the E. So the errors are the E. And some of them have got negative, some of them are positive. So the first thing you do is that you square them. You square each of the errors so that the negatives, or when you square them, it becomes positive. The second thing is after you square the errors, you will sum them together. You sum the errors together. After summing them together, the third thing you will do is you will minimize this error sum of squares. So you will minimize this error sum of squares. Now, anytime you are doing a minimization, we have entered into the world of optimization. So you normally will minimize subject to some constraints. That principle is trying to say that you are reducing the errors above and the errors below to a lowest value of 0. That is the technique of regression. It minimizes the error sum of squares so that we'll be able to have a clear interpretation of the variables. Okay, so now let's go back to the notes and then we see what the regression is doing. So the errors are also called residuals, I said. So you can see that there's a data point here, and in this data point, there is a residual, an error. Because if the error measures how far you are from the line of best fit. Now, the essence of regression is to minimize error so that you can use it for proper interpretation. Now, when you have estimated the model, you will get the predicted model. The estimated model is also known as the predicted model. So the predicted model is y minus y cap. Okay. So y is the actual or the desired. Let me just write it here. So you have y minus y cap. You just write it down. You also have to write it down. The y here is the actual values. So I take this particular value. The y cap is the value you are expected to have for that y. Okay, the value you are expected to have for that y. If the gap is between them is 0, it means they are the same. That's why the gap between them is 0. And therefore, there is no error there. But if the y is bigger than the y cap, then there is a positive error. If the y is smaller than the y cap, then there is a negative error. In either of them, your goal is to minimize the error sum of squares. Okay. So all that I said is partly here. And this is where you have to pay attention because there's some theoretical backing here that you are expected to derive, in your test. So you're going to minimize the error sum of squares or the residual sum of squares between the actual and the predicted. Like I told you, the predicted is also called fitted. Okay? Is a y cap. Is a y cap. And the y cap, you're going to find it to be very interesting. So watch this. Watch this, guys. Watch this. We are looking at simple regression. Simple regression has y equals to, well, let me use small letters. Simple regression has y equals to beta naught plus beta 1 plus the error. Okay. Now, I can do, I told you that the error is the actual y minus the y cap or the predicted y. So watch it all. I can substitute this y, this actual y, because the actual y is this, which is the whole of this. So the error is actually the whole of the beta naught plus the beta 1. Sorry, beta 1 must have x. Plus the beta 1x plus the error minus the y cap. The y cap is the part before the error. Is a part before the error. So the y cap is going to be beta naught minus beta 1 x1. Okay. So this error is going to be equal to that. But we are not interested in this because at the end of the day, this error will have to, in fact, the original model is this. This is the original model. So if I were to make it the subject, I'll move the whole of this to the left-hand side so that y minus beta naught minus beta 1x be equal to the error. And that is why we say that this part here is a y cap, whereas this is an actual y. Okay, so keep in mind that with this principle I just taught you, you can use it to derive a beautiful matrix here. Let's assume that we have y is equal to beta 1. The error, I can use any one of them. So watch here. So I said y is equal to y, epsilon is y minus y cap. And I can substitute the whole of this, which is a y cap. Or it's just a matter of this one here is just a matter of making the rest the subject. Okay. From here, if you make it the epsilon the subject, you will get this one. So you group like and you move everything away from the epsilon. Okay. Now, at this stage, pay attention. I took the square of the error. So that's what you see here. And I demonstrated it earlier. And then I summed it. That is a sum. After summing it, I optimize it. I optimize a function. And by optimizing the function, you differentiate everything with respect to the beta naught. And then you come and differentiate everything with respect to the beta 1. Pay attention. Pay attention. How do you differentiate this one with respect to beta naught? Well, you just write the partial derivative of this whole thing, okay, divided by the partial derivative of the beta naught. Now, when you differentiate this very one with respect to beta naught, remember that there is a square here. So that square will multiply the y, giving you 2y. And then, of course, there's also epsilon there. So if you differentiate with respect to that one, it will be 0. Okay. So I've just used the 2 to multiply the lambda here. Okay. If I use the 2 to multiply the lambda here, technically you're going to get 2 lambda and then y. So technically this y shouldn't be positive, it should be negative. It shouldn't be negative, it should be positive. Then you take the 2, there's 1 in front of the beta naught. So you multiply the exponent 2 by the index of 1. You have 2 beta. Then you subtract 1 from the exponent. Okay. That's what we are actually going to do. So we take these 2 to multiply this one. And then we multiply through by the outside parameter. In other words, we are expanding. So when you take the partial derivative with respect to b naught, this is what you get. You get this one. All of them have got the 2. Okay, check a positive and a negative. You set it to equal to 0, and then your goal is to make beta naught the subject. Like technically from here, if I want to make beta naught the subject, I'll divide both sides by negative 2. So the 2 will go. You'll be left with what? Summation y plus sigma beta naught. Okay, the 2 are gone. Now I want beta naught. What do I do? Well, if you want beta naught, you can divide all sides by the sigma. Okay, if you want beta naught. Okay, but one first way you can do is that you can move this one. But remember that the sigma is once. Okay, it's a sample size for the beta naught. For the other ones, it's not a sample size, it's for X or Y. So if you divide, it's actually the sample. So what I mean is that, check here. If you take this one, okay, this summation is actually n samples. Okay. So instead of dividing both sides by summation, you are actually dividing both sides by all sides by n. So you take this y here, negative y here. You take this negative y here, and then you divide it by what? By n. So you're going to take this one here, you divide it by n. And then you take this one, divide it by n. bring the beta 1 out. When you do that, when you have sigma y divided by n, that is actually y bar. That's actually the mean of y. Okay, so that is why sigma y divided by n gives you what? The y bar. And then if you do this one here, you have sigma, in fact, let's bring the beta 1 out. So you have beta 1 out, sigma x, also divided by n, that will give you x bar. So it's just like the sum of the x divided by the sample size. But in the case of the beta naught, okay, it is just like dividing the sample size by itself. So you're going to have the sample size. And then that sample size will cancel because it becomes n by n and n by n. In fact, what I mean is that this sigma beta naught, if you divide it by sample size or sigma, okay, if you divide it by sample size or sigma, it's like they cancel. We are left with sigma, beta naught. That's it. And therefore, once you do that division, you can pull out the beta naught, as you can see here. Beta naught now, if it stays here and this one goes to the left-hand side, you are left with beta naught. But now this beta naught is an estimated one, no longer a parameter. It's an estimate. It's not an estimator anymore. And therefore, beta naught will be equal to the y bar minus beta 1x. What is this? This is going to give you the value. If I know the values of x and I substitute, I can get the value of beta naught. Okay. But unfortunately, beta naught has also gotten beta 1 there. So it means I need to find beta 1 before I actually get my beta naught. How do you find your beta 1? Well, let's go and check. It's just a matter of differentiating the whole thing with respect to beta 1. Just as we did for the beta naught. So here, I differentiate the whole of the numerator, that is the error sum of squares, by beta 1. It's similar to the other one we have. Okay. You bring negative 2 in front, okay, and you also bring negative sigma x. Now watch it. You're going to expand from here. You're going to expand this sigma x. Now some of your colleagues have dropped out. Tell them to join back. Okay. It's all there. So here, you multiply this one by the y, you get sigma yx or xy. But there's 2 there. Then you take the same one, multiply by this one, you get that. You take the same outside value, multiply by negative beta 1x. It becomes positive because this is already negative. So it becomes positive, 2 and beta 1 sigma x squared. Remember, there's x here and there's x there. And so the 2 x's will square. That is why this one alone has a square. Okay. At this stage, you can just divide all through by negative, what do you call it? By negative 2. And everything will clear. The 2 will clear. Those that are negative will be negative. For example, if you divide this one by negative 2, this will go. If you divide this one by negative 2, this will go. And then if you do that, this will go. But then this is already positive, so it becomes negative. This is already positive, it becomes negative. Okay. And this is already negative. So if you divide it by negative 2, it all cancels out. Okay. Now, at this stage, you are looking for beta 1. So you group like things. So everything here should stay on come to the right-hand side. Okay. So here, I just group like things. And then this one will come to the right-hand side. And then the second one will be the beta naught. I've just moved this one. I've kept it here and then brought these ones to the right-hand side. These ones to the right-hand side. So they are all on the right-hand side except this guy. And the 2 has also been cleared. So now I have this guy here, beta 1 there, equals to sigma yx, which is from here, and then minus beta naught, which is from here. I factorize them now. I expanded them now. Group items. So At this stage, you want what? You want beta 1. So you divide both sides by sigma x, x2. You divide both sides by this value. That's the whole idea we are going to do. But I'm breaking it down small first. First, let's do some manipulations here on the right. You see, on this right, your sigma yx is still here. But then here, this beta naught, okay, you have sigma x. The beta naught alone, if you can remember, we had the value. We had the value to be y bar minus beta 1x. So I'm substituting that y bar minus beta 1x. And then now I will expand it with this, because this one is multiplying both the y bar and then the x bar, the beta 1x bar. I'm going to expand it. I expand it here. Watch it. Watch it. I'm going to expand it. I'm going to expand it. I multiply this one by that. But this one is y bar, but now I bring it down to sigma yn because it's the same as sigma yn. And then this x, sigma x is here. And I use the same sigma x here, multiply it by the beta 1x bar. So I do that because this one is actually this very little one. It's actually sigma x over n. Okay. So now the numerator will have sigma x and then sigma x. That's why you see that you have sigma x squared. Then the denominator will have over n. You have beta 1 here. Okay. Now you have beta 1 here. And there's beta 1 there. So you have to group beta 1. So I move this one whole bam to the left-hand side. And then factorize out the beta 1. So when I pull out the beta 1, the rest, which is starting with this one, and the one I brought from here, they will be in the bracket. What about the right-hand side? The right-hand side still has this yx, summation of yx. It hasn't changed. Minus the other bit doesn't change. The final manipulation is that I can now find my beta 1 out. When you find out the beta 1, you're now left with this summation. Summation x, I mean, it's just like when you divide both sides by this, and divide both sides by this, the numerator you will see left here, that is all you see here. And when you manipulate and cancel easily, this will fall down to this value. This value is the actual value for beta 1. It tells you how much the y changes when all the x's have changed. Congratulations. You just derived the OLS beta 1 mathematically. And you should learn how to derive both of them. Okay, so that is it. Once you derive it, this gives you the normal regression. Okay. So the entire regression is actually given by this. Okay. The entire regression, this beta, okay, for the OLS, let's say for the OLS, because the other methods. Okay, that beta OLS, that is the value. Yeah. So once you have X value and Y value, you can substitute them and use this matrix to simply find your answers. Okay, but there's another approach you can use to solve this, not only OLS. There's another approach called regularization approaches. They are very good if you want to deal with non-linear situations, or if you want to handle multicollinearity. We'll look at multicollinearity. In fact, we've already mentioned it, but we'll look at it deeply very soon. So one of the regularization approaches is range regression. You can go through range regression using this formula, okay? And then you can minimize this objective function. Now, the only difference between this range regression and the OLS is this. Watch it. The OLS is this part here. I've just used different notation, but don't worry. Remember that the OLS, we had the error. So this whole thing is the error. And then we square the error. And then we sum them. That's it. So the OLS part is here. The ordinary least squares part is here. But I've added a regularization parameter here. This parameter is what makes the thin range regression. You add another parameter. And watch the parameter is lambda multiplied by the sum of beta squared. Okay. That's different from lasso. Lasso regression, it also adds something to the OLS. This is the OLS. But what it adds is not beta j squared. It is rather the absolute value of beta. These two are very, very important when it comes to your long essays in research. But there's a third one that combines the two. You see, this first one, it just took beta squared, sum of beta squared. This one took sum of beta bar, sum of beta, or not sum of beta absolute value. That's what it's actually taking. And now the elastic net is going to add these two together. Watch it. All of this, some of them might say that what is the use of all these things? Don't worry. You know the use of them. Only are using them practically. The elastic net will still combine the two. See, one of them was beta j squared. The other is beta j absolute value. And that's all. It adds these things to the original ones, and then you can include your ordinary OLS, and then you add sorted. The goal is to find the betas. That's the whole goal of regression, is to find the coefficient, and interpret them, make them make sense. Interpret them, make them make sense. There is even another one. Just watch this. It's a simple one, but it's also very, very important because, again, it has other advantages. It's called support vector regression. In the support vector regression, it's just like the range, but the only thing is that here, you are minimizing this function subject to this constraint. Okay. So once again, you can go through all of that and you see that this is what you are minimizing subject to this constraint. If you compare it to the OLS, this is how the OLS does it. This is how the OLS actually minimizes the error sum square. But this is how the support vector regression, which comes from support vector machine, you do that next semester. This is how it writes the minimization or the optimization function. Okay. Now, we are going to do practicals. So let's go to our practical work and let's rock and roll. Let's rock and roll. So we're going to go to our Jupyter notebook. Please open your Jupyter notebook and work along with me. The reason why you got to work along with me is that you're going to do a test and you have to work along in the computer lab whilst I go around watching you. So it's nice that you are working along with me here so that you become familiar with it. Okay. So the data set we are going to be using, you all have the data set, is known as gene regression. It's known as this. We are not going to do the regression today. It's just all the theories we have done today. We are going to practicalize them on the Burkutu data set. Let me see by hands, those of you who have opened your notebook. Okay. Clement has done it. Eileen, Kwachi are very serious. Very, very serious. I mean, your tenacity is beyond recognition. Philip, Tina, Sandra, Ebenezer, Millicent. If you have not done it, don't force to raise your hands. I'm about to ask you some deep questions. So, Samuel, Perez, Paulson, Felicia, Ivy, blah, blah. Yeah, many of you are not following me. Many of you are not following me. Okay. So this is a data set. You have the entire notebook. You can lower your hands now. You are writing a journal paper. It's entitled Determinants of Demand in the Alcoholic Beverage Industry in Ghana. We've said this thing multiple times. We're going to do some kind of first things first. So the data set is this here. The data set is right here. What you're going to do is, this data set has been saved as a CSV file. You see, this is a CSV file. That's why you see gene.csv. Okay, so it must be in your folder. All of you must have the Excel, the CSV file in your Python folder. I mean, your working directory. Okay, so you should know your working directory because that is where you're going to. So you want to collect the data, you can put it in your working directory, unless you want to use the path approach. Working directory in Python Jupyter Notebook. You should all know it. You should all know it. So if you don't know them. Okay. You can find it, wherever it is also, you can find it. All right, so now we're going to run this data to show the top part. I just did. Okay, so it's loading. It's loading. It's loading. Okay, so you can see that my data is showing something here. Now, why is it showing that? Because, and I'll tell you why. Let's go to my Excel. It's not supposed to show that, but it's showing that. Because my sheet here, I have only the P and the Q, you see. So I need to delete this sheet and then use the actual gen data, this very one that I've opened. Okay, so I'm going to run it again now. And this time it should show me the entire data set. There you go. So it's showing me even the shop number 1, shop number 2, and all of that. I can remove that shop whenever I don't want it. All right. Now, this gives me the head of the data, but from your programming language, you can show even the 10 rows of the data. So I just change the 3 to 10. Run it. It will give you the first 10 rows of the data. Please do that and fill it. Okay. Let me see by hands, those of you who have been able to run this command and can see the 10 rows. The 10 rows, not just the 3, because that will indicate that you're on track. This is where it helps me to know those who are following me. Because the last time I spoke to you, you all said you've been using Python. So, okay. So I see 2 guys are on top of their game. If you have a challenge, you can ask a question. But please remember that you do the same thing as a test. So it's important that you are following. Okay. You know, sometimes the temptation will be that, oh, don't worry, I'll watch the video again. It's a different thing when you are doing it on your own and you face a challenge and you don't know how to address it. All right, let's move on. After running and seeing the data, the next thing is create a contingency table. Okay. I spoke about contingency table. Okay. Oh, by the way, before that, let's address some questions in the descriptive because I've set this thing up in exams. So in this descriptive statistics, which variables are categorical? Which variables are numerical? Which variables are float? Which variables are Boolean? Which variables are integers, characters, dummies? Let's start. So who can tell me which variable columns are categorical? Quickly. Raise your hand and tell me. Categorical, which ones? Sylvia.
The location, the occupation, the relationship, and the shop.
Okay. You have joined the club now. There's one more you missed.
1, 2, 3, 4. Shop, location, occupation, and religion. Come again?
You mentioned shop earlier.
Yes, please, I did.
Okay. So that was shop. Very good. Which variables are numerical? You can tell us. Which variables are numerical? Who can mention the numerical variables? Millicent.
LPC.
Okay, which variables are float? Now it's getting technical. Which variables are float? Aline. Wrong. Let's go to Perez. Perez, flow.
Yes, sir. P and M.
P and M. That's the correct answer. P and M. You don't understand, Axel. Let's continue. Which variables are Boolean? Have you guys done analytics, programming? Yeah, I'm sure. If you have done Python, you know this. Yes, Boolean. Patrick?
I'd say location because of the urban and rural. But I'm still not sure.
I know you are not sure. But you have the idea. Okay, it is that one. Which variables are integers? Integers. Integers. An integer is a positive or negative or number. Clement.
Q and C.
Q and C. All right. Which variables are characters? Characters. Characters. Imagine you have a small data set and check my last question, last year, so you see. Ask you all this. Characters. I should give that one to you as a homework. But it is a homework. Which variables are dummies? Patrick?
Yeah, dummies are 0, 1, 2, 3, 4, 5.
Which variables are dummies?
Sorry, the shop rather.
The shop are dummies. No. It's not a shop. Easy.
So please, location, occupation, and religion.
Very good. So note that the location, occupation, and religion plus the shop are numerical, but only the location, occupation, and religion are dummies. Sorry, did I say are numerical? Are categorical. Okay. Location, occupation, religion, and shop are categorical, but only the loc, occ, and rel are dummies. Okay, let's go to contingency table. Okay. With contingency table, we are able to check important link, relationship between the data sets and some of the variables. It's very, very useful in machine learning. So let's look at how to do that. This is called cross tabulation. So you can use PD, okay, the pandas, dot cross tab. The name of our data set is DF. Okay. And we wanted to classify the number of data points in religion against location and against occupation. So you run that and then we see the result. Let's run that. Let's see that. Okay. So now you can see the results here. You have some beautiful results there. Question number 1. How many Buddhists are here? The first one. Looking at this contingency, how many Buddhists are here? Let's do sharp. How many Buddhists are here? Kwache?
8.
Sorry?
8.
8. Wrong. Richard Ban, how many Buddhists are here?
12.
12 Buddhists. Okay. And the answer is that when you look at the Buddhists, it's not only that column. It's not only this column, this row. It also includes that row because the Buddhists we have Buddhists who are living in rural areas and we also have Buddhists who are living in urban areas. Next one. How many fishes are Christians? How many fishes are Christians? You can raise your hand and tell us. Someone. Richard Ban?
The 8.
Is 8. But actually, how many fishes are in this data set? before the 8. Clement.
16.
16. That's wrong. Oh, yeah, that's correct. That's correct. 16. Very good. Because when you look at fishes, you go through this column. That is 4 plus 4 plus 8. Now, next one. These are preliminaries. How many teachers are Muslims in the rural areas? How many teachers are Muslims in the rural areas? Sylvia?
4.
Hmm?
4.
4. How many Christians are here in this data set? How many Christians are here? Aline?
12.
12. Very good. So guys, that's it. If you don't understand, your contingency table you have is way more than this. The categories are like 9 by 8. So you should be able to understand the nitty-gritties in everything. You will also be given an assignment. You do the same thing. Next. Descriptive statistics. You can find the mean. The mean and the median and the mode that we found in the Excel, we're going to generate it. To do that, you use the describe command. Now, the .t means that I want this command to be transposed. If I don't bring the t, the count here will not be at that top. It will rather be down here. It will rather be on the far left. And then those on the far left will rather come up. So the t will transpose the data set. And it will also round them to 3 decimals. So let's run this, you get that. Let's change the decimals to 6 decimals. And check the data set, it will change to 6 decimals. If it has, it will bring it. If it doesn't have, no problem. Okay. Now, you can be given this and then you interpret, or in your assignment, you can be given this to generate. Or in your long essay, you generate yourself. Okay. So what can the mean, the median, and the mode tell you about the distribution of, oh no, I made a typo here. Okay. It is about the distribution of Q and P. Q and P. So let's look at the mean for Q. If you look at the mean for Q and the standard deviation for Q, what does it tell you? The mean is more than the standard deviation. The mean is more than the standard deviation. The mean is more than the standard deviation. So it means that there is not much variability. There's not much variability when it comes to the quantity demanded. Okay. The data points are not so varied among each other. Okay. Next one, when you look at price is 15, the mean is 15, the standard deviation is 1.2. Okay. So it tells you something. In fact, you should edit this thing. It's just a mean and the standard deviation. The standard deviation. Now, this thing gives only the mean and the standard deviation as well as some other things. It doesn't include the median. So there's no need to include that. It's a mean and the standard deviation. But the clue is this: anytime the mean is bigger than the standard deviation, it means that there is not much variability. But when the standard deviation is more than the mean, there's a lot of variability. There's a lot. This question I keep asking, so please take note. There's a lot of variability. There are a lot of variance when the mean is less than the standard deviation. Okay, so this was descriptive statistics for all the 40 samples. That is why you see that count is 40. But what if you want the descriptive statistics not for all the 40 samples, but for a few groups? For example, I want the location for those that are across different religions and across different locations. I want their quantity. So look at it. Among the Buddhists here, okay, it says that what can you say about Christians in rural area? And and the average Muslims in urban area and rural areas given their standard deviations. So if you look at Buddhists, for example, the Buddhists are 8. The average quantity demanded is 170 bottles. The standard deviation is 2. So there's a 21. There's a less variability among this in the rural sector. Okay. Now, in the urban sector, you can clearly see that they are all perfect. The urban sector, they are all almost, how many are they? They are 4. And they are all almost having the same data. If you go and check the data set, that's why the standard deviation is 0. Okay. It's perfect. So if you go and check the urban groups, just the urban guys among the Buddhists, you see that they all have the same value for their quantity demanded. The next one is the Christians. The Christians are 12. The average quantity demanded is 206. And the dispersion is 13, which means that there is less variability among them. That's it. We also looked at normality. Okay, normality. We indicated that you have to use a work, Shapiro work. But one thing you can do with Python is that you can check whether each variable is normally distributed. So we're going to check whether each variable is normally distributed, but we just check only Q. You can do the rest later. To do that, you have to import a package or a library known as Seaborn, and together with the matplotlib, pyplot. Okay, you can use that. We can draw a simple histogram for the quantity demanded, and even I'll tell Python to introduce the kernel density plot or the kernel density estimation, superimpose that on the histogram. So we do that. This is the command for that. SNS is the Seaborn command. We call it histoplot. The name of the data is DF. The x-axis is Q. Okay, the kernel density true means that you want it to show the kernel density. If you say false, it will not bring the kernel density graph, the normal distribution curve. Okay. It's actually, this one is not indicated that it is normal distribution curve or not, but it is the distribution curve. And you indicated that the color is red. The edge color, you indicated that is black, and you can see that the edge color is black. You can change the color from red to blue, and then run that. It's loading. It's loading. Oh. I have a lot of things open. But I just hope that you have the opportunity to follow me to know exactly what you're doing. Yes, sorry.
Sir, please, our programming class, we haven't gotten to all these you are doing. So some of us, we are not able to.
That is why you are not the one coding. You can see that the code I gave you, if you have it in front of you, you can just, you're not even coding, you're not even typing it, you're just running them. Are you aware?
Okay.
Are you aware?
Yes.
Are you aware you can just run them?
Yes, I know you can just run them.
Yes. Okay. You see, my color has changed, but I hope you are running them. What color did you use? Did you maintain my color or you've changed your color? Who has changed his or her color? Guys, the command I gave you, you are not supposed to do anything. You're supposed to just understand what I'm giving you and run them. Just be running them by heart. What color did you use?
Yes, you asked orange for the blocks and blue for the edge.
Very good. So here's the thing. I will give you in exams, I will draw something like this. After giving you a story, I'll draw something like this. Then I'll tell you to interpret this result. So that's why we are about to interpret this, so that when you get it, you also learn from it. Okay, so first thing is that is Q normally distributed? Looking at this data. Who can tell me? Looking at this graph for Q, is it normally distributed or is it not normally distributed? And what makes you say that? Okay, so first of all, Q is not normally distributed because we know that for a normal distribution, first of all, the kernel density plot is like this. You all did normal distribution in probability. You remember how the curve looks like? It looks like something like this, if you can remember. Just one peak. Just one peak. But the one we have has how many peaks? It's not unimodal. How many modes does it have, the one we have here?
You can say 2. Wait, sorry.
Ebenezer and it has 2 modes. So it's not unimodal, it's not multimodal, but it is what? Bimodal. It's bimodal. Bimodal means the modes are 2. Very good, Ebenezer. I hope you have it. The next is, so you can see that you can use a kernel density plot to determine that. The next is to also put all graphs into one. So sometimes instead of doing one big one like this, I can put multiple graphs into one. So I use the same Seaborn, okay, and SciPy stars command. You mean you haven't learned this, you haven't done this. At least I'm giving you a template. So next time you use my template to learn the rest. You can create all the axes in 4. So watch here, I've indicated that create a figure with 4 subplots. So this is a 2x2 grid. So the graphs we are going to draw using this, you're going to have one like this, one below it, one on the right of it, and one on the right of the below one. So that is a 2x2 fixed size, which I have just indicated. But I'm just explaining it to you. But the top part actually explains it. It says create a figure with 4 subplots. 4. And then the first figure is a histogram. That's it. The second figure is box plot. The third figure is kill plot. You are not doing your proper work. That statistics you were doing previously, you are now entering into the proper statistical world. So pay attention. Instead of saying that we've never done it, there's a first time, and this is the first time. Kill plot and then density plot. Now, how do you interpret them? We already know about the histogram. I won't talk about that. The first one. The last one, the kernel density plot. We also have explained them. There are only 2 of them that are in the middle, box plot and QQ plot. Let's run this. First of all, I go through each one of them step by step. So you just run this and let's see the results. So should hopefully show, because there you go. So I changed the color to green. This one, we've already spoken about it, the green one. But I want you to look at the box plot. Guys, what is a box plot? A box plot is a plot for comparing 3 categories, 3 groups, based on their something. That is numerical. So in this case, I am comparing 3 groups based on what? Religion, isn't it? So if you look here, my groups are based on religion. Okay. As you can see. And I have 3 different religions. I'm comparing each one of them, the quantity demanded of gene betas. And when you look at the graph, these are Muslims, these are Buddhists, and then you have the Christians on the far right. The question is, which one of them consume a lot of akbetesh? Just looking at the graph. Well, the only way you can do that is look at the center black line for each of these boxes or groups. Each of them has got a center black line. That black line is the median. Write it down. That black line is the median. So when you look at them, just using the median, you know who are the heavy drinkers. Who can tell me? Who are the heavy drinkers? Which religion? Patrick?
The Christians,
How do you know that?
because their black line is the highest as compared to the other ones. It is close to 20.
And that black line is called what?
The median.
So their median is the highest. Followed by which people? Christians followed by which people? Patrick?
Followed by the Buddhists.
Exactly. So by just the graph, when I tell you a question, just looking at the graph, you can use it. Now you got to learn a little bit about this graph. Apart from the median, the top part of the graph, the top part here, tells you the 75th percentile. And then the bottom part tells you the 25th percentile. Now, your basic statistics will tell you 75th percentile and 25th percentile, what they mean. But if you check it very carefully, which of these lines, this median, the median is actually the 50th percentile. Write it down. You see, the problem is that you always want the thing to be given to you. You should write it down and make your own note. So the median is the 50th percentile and is a black line in the box. Now, if you look at each of the boxes, it is Muslim that has the median dividing the boxes per, if you check. The others are not, which means that majority of them, because if you look at majority of them are actually consuming more alcohol. So they are not only consuming more alcohol, but majority of them are consuming. They are not consuming more alcohol compared to the Buddhists and the Muslims. But if you look at the Christians, majority of them, because the center line is supposed to be in the center of the box. The black line is supposed to be in the center of the box. But it's not in the center of the box, like the Muslims. That is where you can now indicate that majority of them who are consuming the alcohol are really consuming the alcohol. Okay. Now, sometimes a box plot will indicate some things at the top here, some things at the top here, above the box or below the box. What are those things? Those things, what are they? With a whisker. This is a whisker. It's
The outliers.
the outliers. Very good. Now, another way you can show whether the data is normal, apart from the histogram and the KDE, another one you can show is the QQ plot. The QQ plot. If you look at a QQ plot, the straight line, you want the blue line to be fully seated on the straight line. I'm explaining to you how you should always explain. You want the blue lines or the blue dots or the blue data point to be snugly fitted on the red line. If they are not, the data is not that normally distributed. If they are, the data is that normally distributed. Does it make sense? So that is it. So if you look at this, looking at it carefully, for quantity demanded, because majority of the blue dots are not seated on the red line, it means that Q is not normally distributed. But of course, we know that from here. The fact that it has bimodality clearly shows that. See, these kind of words I'm using are the same words you got to use to interpret. Okay, the last one is a density plot, which is the same. So this one we didn't even include the histogram. We just drawn a normal density plot. And when you look at the density plot for Q, it's not normal because it has 2 peaks in there. That is why. So the question we're addressing was this: what do the graphs tell you? That's what we've spoken about. We kept saying it's not normally distributed, it's not normally graphically, but is that true? So to check for normality, you got to use the Shapiro test. That is the next question. So we run the Shapiro test here. Run this command, and when you run it, you'll get this Shapiro statistic. That's what you get. You will see that the Shapiro test statistic is 0.91, and the p-value is less than 5%. Now here is a rule. Write it down. Whenever the p-value is bigger than 5%, or it is 5%, when it's 5% or more, the data is normally distributed. Take note. When it is 5% or more, the data is normally distributed, which means when it is less than 5%, the data is not normally distributed. And when you look at our own, it's less than 5%, the p-value. So it means that that's why I've written the answer that there's a statistically significant evidence that the distribution deviates from normality. In other words, it is not normally distributed. Okay, we are left with the last thing for today, and that is the correlation matrix. The correlation matrix. We just looked at the theory, and we are going to create a correlation matrix. What is that? In fact, let me just go back to Excel. You can do a correlation matrix beautifully. The same thing, we went to the top and did data. And then on the far right, we chose data analysis. And then we did the descriptive statistics. Now, we will do the same thing for correlation matrix. Instead of descriptive statistics, you double-click correlation. Double-click correlation. Come and click. And when you click correlation, you see input range. Just click on the numerical variables. Don't look at the category. Click on K, drag it to M, and then move all the way to the end. Okay. That's it. And then check the labels. Because when we're doing it, we selected the first information. So you click on labels, and then you click on new worksheet, and then you can type the name you want. A new sheet will be created. Or I just type call. You can type even your name. And then you click OK, a new sheet will be created. This new sheet that has been created here is what is known as a correlation matrix. If you want it to 2 decimals, click on home and go and change the general you see here. Change the general to number, and everything will be in 2 decimal places. Like that. So this is a correlation matrix. We want to do the same thing in R, in Python. We want to do the same thing in Python because Excel doesn't give us the p-values. You see, anytime you want to know whether something is strong, you check the p-value. We just did that for normality. So come here. Okay, so we're going to use Jupyter Notebook for that. But Jupyter Notebook, in the data set, you have something called categorical. So you have to remove the categorical variable first. So here you will type, this is an instruction that says drop the non-numeric, the categorical columns. So this command will drop it. It will create a new column for the numbers. It calls it new, it calls it calls. Then it will put a correlation matrix on them, create a data frame for them, and then indicate the p-values using the Pearson's product moment correlation coefficient. It will create an annotation matrix, and then you create a beautiful heat map, and it will title it. I've written that you should title it. So do all of this here. Let me run this one. And you can Run it. Okay, so that's it. So the beautiful thing about this is I watch it carefully. It tells you the correlation. So if you look at Q and itself is on the bottom. Q and itself is perfect. So that's why the correlation coefficient is 1. In fact, I have a series of questions about the correlation I want to ask you. So Q is perfect because correlation and yourself is 1. And you can see that the p-value is 0. Anytime the p-value here is 0, it means that the correlation is significant. Anytime the p-value is 0, the correlation is significant. Which correlation would you say is not significant from this data? Which correlation would you say is not significant? All of them are significant. Talk to me. Don't type to me. Talk to me. Yeah, question.
The one with the value of negative 0.51, the p-value there is 0.001.
Yeah, so the p-value
Since it's not 0.
So if we're looking for perfect, significant statistically, it is that one. But then the rule is that once the p-value is less than 5%, the correlation is significant. Now, if the p-value is less than 1%, the correlation is also significant. But you want the p-value to be less than 0.1%, okay, or less than 0.01%. That is when you know that the p-value is highly significant. It's highly, highly significant. That is when you know. Do you understand? The one who answered that 0.001. Okay.
Can I please go back?
So I'm saying that if the p-value is less than 5%, that's good. But if another p-value is less than 0.1%, it's better than the one which is less than 5%. Okay. So let me give you an example. Let's say that you have a p-value, and this p-value is 0.3. Sorry, 0.03. 0.03. Is that significant? Is that correlation with this p-value? Is this significant or is not significant?
It's significant.
It is significant. Okay. Now let's say that another p-value is 0.002. Compared to the previous one, whose p-value is, which one then two is significant? It's more significant.
The 0.002.
Why?
Because it is lesser than the 0.03. If the percentage is lesser, then it becomes highly significant.
Exactly. So the lower it gets towards 0, the more significant it is. That's the whole point.
Okay.
Lower. So all of us can be below 5%, but I am way below 5% than you. Then it is that my correlation is more significant.
So what are if it is 0, completely 0?
It is the best.
Yes. Okay.
If the error you made is 0 errors, you didn't make any error. Some people, they don't even raise their hand to ask question. The only thing they will do is that they will go and type things like, Frederick Owusu. Like, on this serious, what is, Like, go over the thing by, and by the way, anytime you ask the question that go over the thing, you've not spoken. You have to raise your hand and explain which part the person should go over. And if you can't write that, you don't type, It's like you people are always entertaining negative molecules into your body. I keep saying this, that every cell in your body is eavesdropping on your internal dialogue. You don't understand that grammar, write it down, you'll understand. Every cell in your body is eavesdropping on your internal dialogue. So the more you keep saying, it's not easy, oh, hey, it's hard, things like that. The moment you give your brain those statements, you are doomed for life. It's not good at all. Don't speak negativities into your life, because your subconscious mind does not take anything for a joke. Okay. Now, which one is the most negatively correlated variable? Okay, let's go to the question. By the way, these p-values, that this heat map we generated, you could have used this command to generate the correlation just like this, and then the p-values will be at the bottom. I don't like this. I like the heat map. The heat map, the values are inside it, so it's cool. This is another heat map. In fact, you can run them later and see. This is another one. It's much more compact than the previous one. And that one too has got the what? The p-values in addition to the coefficient. It's really cool. Now we are ready to ask our question. Question number 1, which 3 pairs of variables are perfectly correlated? The first one is Q and Q. The coefficient is 1. So if you match Q against Q, they are perfectly correlated, this one and this one. And therefore, is one of them. Which other pair? P and P. Which other pair? M and M. All of them correlation coefficient of 1. So a perfect correlation is the one with a correlation coefficient of 1. That's it. Next part. Which 2 pairs of variables, I'm reading this, which 2 pairs of variables exhibit high correlation with the response variable? So which 2 pairs of variables exhibit high correlations with the response variable? By the way, which variable is a response variable? Who can tell us? Which variable is a response? The response variable is also the dependent variable. Yeah. Which variable is that? Which variable is a dependent? The variable where the others depend on, or the variable that is usually influenced by the others. In our data set, in our matrix, which one is that? The Q. Okay. So the correlation between P and Q is negative 0.87. That is the one with the highest negative correlation in this context. Next one, it says that what does that tell you in terms of predictive potential? It means that price has got a higher predictive potential than the rest. Are they statistically significant? Come and check the p-value for price. If you check it, it is 0.0. Yes, they are statistically significant. Next, which 2 pairs of variable may be multicollinear? Yes, Richard. Which 2 pairs of variables may be?
Please, I think your network is breaking. Sir.
Okay. Can you hear me now? Which 2 pairs of variables may be mostly multicollinear? Now, the last time, okay, maybe not here, but we've done it in other places. Write this down. Write this down. Multicollinearity exists when 2 independent variables. Multicollinearity exists when 2 independent variables are so highly correlated that 2 independent variables are so highly correlated that it becomes difficult to disentangle the partial effect of one from the other. It becomes difficult to disentangle the partial effect of one from the other on the dependent factor, on the dependent variable. So multicollinearity exists when two independent variables, not two dependent, not one dependent, one independent, no, two independent variables are highly correlated. So looking at your matrix you are seeing here, which two independent variables are highly correlated by looking at their correlation coefficient? Which two independent variables? Which two independent variables? Now remember, you will not look at the column that has the dependent column. So if you look at this column here, here is there. If you look here, here is there. So your information you're looking for are just those ones in this corner here. The one with the most highly significant coefficient, that is the one that is mostly multicollinear. Which one is that? It is negative 0.74. Negative 0.74. That's it. And then it's the variables connecting to that are price and complement, P and C. P and C. The next one after that is which one? Let me see whether Ebenezer will practice. The next one after that is going to be which one? Yes, Richard.
And negative 0.51.
Negative 0.51, no. See, we are talking about highly mostly multicollinear. So you take the biggest one, not the smallest. It is the biggest number you are going to look for. High multiple, biggest number, low multiple, smallest number. And is it?
0.71.
Good. It is 0.71. And that is the one that is the next most highly multiple. Which variable would you say is the least correlated? Wait, the least correlated variable. The variable with the least, if I look at the question, which pairs of variables are least correlated? I don't want you to give me all three pairs. I just want the first pair. Which variable is the least correlated? You see, least correlated is not the same as least multicollinear. If you are taking notes, you are least correlated can be both the dependent variable and another independent variable. But least multicollinear, it is just talking about the independent factors. Independent factors. So least correlated means that you can now include the dependent variable column or row. That's what it means. The dependent variables column or row. And now you can tell me which one is the least correlated. Who can tell me that? Well, the value is 0.61 and the variable is M. Oh no, least correlated, it can be that. Least correlated. The least correlated number is negative 0.51. That is between price and income. That is the least correlated pair. That's it. Now, another thing you can generate is known as scatter plot matrix. Scatter plot matrix just looks at how each variable is scatter plotted. Scatter plotted. And you can see this. You will either see some of them in exams to explain it. For example, just looking at this graph, I can ask you that the relationship between price and quantity, is it negative or is positive? And so you have to look for price. Where is price? This is price. Okay. Where is quantity? You come down here, and this is quantity. Okay, this is quantity. So you're going to find out why price and quantity are meeting. Okay. And when you check price and quantity meet at this junction, you check the graph, you detect whether it's exhibiting negative correlation or positive correlation. Now, guys, when you look at it carefully, which correlation is it exhibiting? Who can tell me? Which correlation is the one I've circled? Looking at Frederick.
Negative.
Sorry?
Negative correlation.
Okay. What about between complement price and price? What about between price and complement price? What is it exhibiting? I should circle that one for you too. Okay, so when you check it, it is also negative correlation. It's just weak negative. Price and complement. That's where it is. So this can be done using scatter plot method. By running it, you can easily be able to do. That's it for today, for the practical part. Okay. Next time, we will look at the deep side of the regression, and then we'll also try to do the Excel continuation. Ladies and gentlemen, that brings us to the end of the entire caboodle. Any question, please?